and Growy. And next over to you, Jason.
Thanks, Brian. And there's no way that Chris would have put that on camera, so it's a good thing we didn't record it by then anyway. So let me just go ahead and share my screen here so we can talk about, just give you a little update on where we are. I want to give just some level setting for everyone about where we've been thinking with Helix, kind of what the plan was originally, where we are on that plan, and then kind of give you some updates really quick. This will be a very brief presentation, but I want to make sure that I want to have some background before we dive into some of the further discussions. And so, really when we talk about it, we call this DOE's co-simulation platform because it really is. It's been a across the board effort to really bring together a lot of the best in grade tools within the DOE complex to make sure that we are building a co-simulation platform that can handle primarily a lot of the energy type simulations that we're looking for. But as Chris mentioned, it is flexible and allows us to do a lot of other extra things too. And so if you're not familiar with co-simulation, this is one methodology for analyzing really large and complex systems. And it's a method for unifying existing software models or new software models in a coordinated fashion. So it does things like, reaches across different domains, reaches across time, and does synchronization of time, allows different modules to be written in the same or different languages. And it can actually, combine different things that are not in the same network. So we can run them on multiple computers, we can run them across AWS and locally, and things like that. And then what this co-simulation tool does really is acts as the middleware to allow those interactions to occur, and then it basically allows those to influence the behavior of the other pieces of the puzzle. So you're really talking about looking at different parts of the system. You're really allowed to then modify the way the other simulation is behaving and then reflect that modification in other parts of the simulation. But really, down on the very core piece of it, it really does two things. It's really doing time synchronization between the different and then managing data exchange between those. Everything else above that, you'll see in some of our architecture diagrams, there's a lot of stuff that has to happen to make those things happen. There's ways to make it easier. There's ways to coordinate it in different ways. But at the core of it, that's really what we're talking about, is really a time management tool and a data exchange tool. But give a little bit of background on just the history of Helix itself. So as mentioned before, we had our first round of funding coming out of the DOE's Grid Modernization Lab Consortium and GMI that funded the initial development of Helix back in 2016. There was a number of labs and others out there that had been building tools in this direction, and this was a great opportunity for us to each learn from each other, bring it all together, and make sure that we had really just one tool that we were all kind of swimming in the same direction with, and that allows us to build a kind of best-in-class open source solution. We did go open source in 2017 and made sure that ever since then, all of our development has been in the open source so that we, everyone could see all the strengths, weaknesses, warts, and all. But I think that's led to a better tool in the end because it got more users and it got us the ability to interact with people much more regularly. In 2020, we formed what was called the Helix Plus project, which was really focused on not just the core itself, which of course we were continuing to improve and things like that, but also improving the usability of the tool. And so if you can see over here on the bottom right, when we really think about the way that the tool is designed, we have some core kind of platform and application layers that I really call as the engine itself. And then we have these layers above that are the simulators, and then how those actually talk into scenario generators, how do you do configuration and automation and things like that. And that's the kind of that upper layers has been the focus of the last 3 years. Phil and his team, as you'll see, has been doing a lot of work on the application layer and even down to the core layer to make those upper 2 layers much easier to function. But that's been our focus for at least the last 2 or 3 years. And I'm really excited because we're going to get to share over the next few weeks the great progress that we've made. We will, of course, be focusing mostly on what's happened in the last year since our last users meeting. So if we missed some of the great successes before that, don't worry about it. It's because we've moved on to this year. So when we look at what our original design criteria were, which is over here on the left, we talked about scalability. We have reached each of these metrics in here. So we are now scalable. We've seen tests up to actually 5 million federates. So we're quite happy about that, that doesn't seem to be a limitation. We as a team have only personally done it up to about 500,000 federates, I believe, is the cap there. But we have external users that have hit higher, so we're pretty happy about that. We're cross-platform, so we could go on to HPC machines. You're going to see some examples of that over the next few weeks. But Linux, Windows, cloud, workstations, laptops, it is pretty agnostic to it, which makes it really nice in the way that we want to mix and match tools, because we actually know that some tools that we have, especially in the grid industry, will only run on Windows. They will not run it well up on an HPC type environment, but we can actually bridge that gap pretty easily. We've tried to make this very minimally invasive, so easy to use, whether it be lab, open source, commercial tools. We're trying to be agnostic to that, and so we try to make it as easy to use any of those tools with Helix as possible. We built it on kind of a modern software platform. Really think about like the API connections into modern software languages, allowing them to basically then communicate into the software layer itself. And then, of course, like I mentioned before, made this open source as possible. So it is something that you are free to use and modify however you would like. And then we've really focused on trying to get all of the major simulation types that we use within power systems, which is in our case, discrete event systems, quasi-steady state, dynamics, and even some transient models that have been tested out at this point. I would say that probably the place that we haven't gotten to and done a lot of testing is on the electromagnetic models, but I don't think that's really a tooling problem. I think that can handle it. It's more of a modeling problem at that point. And then we've done things like what we've tried to do is things like co-iteration, which is tight coupling between different simulators, which allows them to iterate against each other within a time step and then move forward, and some other kind of features like that. So from all of our original design criteria 6 years ago, we've hit all those. We've actually exceeded most of them and done a lot of other things. As you see over here on the right, this is actually all the tools that we've now confirmed are integrated into Helix. That's all the blue ones there. I would even say some of the black ones are probably blue ones at this point. They've actually been fully integrated at this point. And so, while we were focused originally on transmission systems, distribution systems, and communications, we've also added in things like control layers and things like that allow us to interact with hardware. See things like the ADMS testbed, Voltron, and some of the work that's been done with RTDS and others. And then, as Chris mentioned, there was some things that we just hadn't really planned on, and we said, hey, this is actually a great idea. Let's go ahead and move forward. So there's been a lot of work on the natural gas side, both at NREL and Argonne, to integrate NG Fast, Saint, NG Transient. Some great commercial partners that have helped us with that. There's been a lot of great work with Beam and Polaris to move into the transportation arena. And then even things like, getting in tools like MATLAB and others that make it more generic, things like that. So just some really great things that we hadn't expected that actually opened up and really through these user group conversations. And we now moved to where I think have a much more rich environment than we originally planned. So just kind of give you an example of how tools like Helix are used. So this is a example from a deployed piece of software that uses a distribution solver, a transmission solver, a second distribution solver, a building solver, and a communication solver, and gets all those things to communicate up through the Helix bus. It also brings in different kinds of informational agents that we call these transactive agents in this case, but they're basically little Python agents that are doing control things on the power system. Basically, all these things are communicating to the Helix bus. If you wanted to control, say, a building thermostat set point, you would have Energy Plus here representing a commercial building. The thermostat is over here that's then responding to prices coming out of Pi Power that are then communicated back here. And that all comes in a big loop through Helix to allow it to then change the behavior of the building simulator and then reflect that on the power system. And of course, then have to represent that all through a communication layer. So it allows you to do things, you basically configure these things, so then you're allowed to look at things like, well, what happens if you lose communication? Or what if you want to understand how a commercial building versus residential buildings behave in certain price responsive systems? It allows you to do things like like this, where in this case, we're sending out a transactive price that then modifies the behavior of the buildings, and you can see the overall change in what those buildings' behavior is as a reflection of that price. And we're going to go into the detail on this because we're through our use cases over the next few weeks, we're going to dive into a lot of these and get some more examples about how that works. But just to give you an example of what the kind of software layers look like and how these pieces all fit together. If you can imagine before using Helix, if you wanted to design something that tied all these things together, this is a lot of one-to-one connections that have to be built and maintained, and those connections over time will certainly fail. Having myself started in that area by building a lot of tools that had one-to-one connections, and then finding out that a year later they were broken and you had to start over. The maintenance between the Helix layer and these layers is significantly easier and significantly reduced costs to get there. So part of what's great is that there's just a lot going on in the community right now. This is just a list of projects that our team is very related to, in terms of we've got folks on this call that are part of these. I know for a fact there's at least 20 other projects out there, maybe even 30 or 40, that are using Helix across a wide area of projects. If you want any information about any of these tools or any of these projects, just let one of us know, and we'll happily get information to you. But I kind of summed it up in some areas of where we're really growing, and so some of the big areas are transmission and distribution, kind of impact modeling, transportation and grid, any kind of new control system and grid models. Natural gas and grid is a big area of growth and excitement there. Really cybersecurity and anomaly detection, being able to put in different kind of actors into the system and looking at those behaviors. I call it techno-economic analysis, so combining economic and power system models. And then I think the biggest one over the last couple of years has been trying to tie it to hardware in the loop. So actually like getting Helix to be able to stay with wall clock time and then work with tools like RTDS and OpenRT. So what's kind of the big recent things? I would call so release 3.1, I believe we had in January of last year. I would call that like our Windows XP. That was the first, what I'll call super stable, super user-friendly version of Helix. Not saying 2.0 wasn't great, but it was really the core engine itself. And then over the year of that one, we really focused on getting some of the user requests added in there. Till really spring of 22, this last year we released version 3.2, where we added a lot of translators, new timing capabilities, REST APIs, really starting to add features that folks have been requesting to try to do specific simulations. Version 3.3 in the fall, we had just a number of small bug fixes that are kind of built up. Nothing major, but just kind of a lot of small ones that had added up over time. There's new iteration support, and then getting ready for some of the multi-site demonstrations got added into there. And then version 3.
No, we got about 2 minutes left.
Yep. Version 3.4 just released this last month, really about dynamic federations and being able to like reconfigure simulations on the fly. Some new tools like wildcard matching in terms of how to link up your tools, and then what we call a data sync interface, which Phil will go into more detail here next week. But really just, as you can see, a lot of these things are not about the core engine itself, but actually how users use the tool. And that's really been focused on it. And part of that has also been trying to add documentation. So we've added a lot of user documentation. We've created a set of common domain APIs that we hope folks will start to use. And then a lot of developer documentation has been pushed out there. And of course, documentation is great, but if you don't have use cases that show how to use those, that's really hard. So what we're going to do over the next 6 weeks here is really talk about the use cases that have been developed, including a user exchange form that we've created that's been really helpful for folks to learn from each other. The culmination of that, Brian mentioned, is a multi-site co-simulation demonstration. We're really integrating multiple of those use cases. And to me, what I thought was also important was where we're really going to introduce some of these standardized domain interfaces, which is really kind of a set of standardized naming and semantics that allow us to say, hey, if I'm going to have distribution simulator A and B, when it comes into the Helix tool itself, they look about the same, so that no matter how I connect a transmission tool to it, it doesn't know the difference between what's behind it. And so that's not there yet, but we've been able to at least show some demonstrations of how we could get there. The community has been wonderful. There's at least 8 journal papers that I can find in the last year that are not coming from the core Helix team, but from users that are around us. And that's across all these areas that I just mentioned. So it's been really, really interesting to see some of these things come out and find out, folks that are using the tool that we didn't even know about. There's also been presentations and of major conferences that I've listed here, and then we've got a tutorial scheduled here coming up in a couple months at the Open Source Model and Simulation Energy Systems Conference that we're hoping to show folks a little bit more about how to use the tools. And so I'm not going to dive into this. This is our seminar series coming up. Brian had a much better picture of this anyway, so I will dive into there. And from there, we'll leave it to end with any questions you might have.
Awesome. Thanks, Jason. We have about 4 or 5 minutes for questions and around the overall project or anything like that. And we'll switch over to our first in-depth use case.
Well, so if there isn't anybody else who's just dying to ask a question, I put a question in the chat, and so there's been some work that's been going on at Oak Ridge about under the DARKNet congressionally directed activity on alternative timing sources, and there's some concern about using GPS as a synchronization time source and some vulnerabilities associated with that. But it got me to thinking, is like, if Helix is the time orchestrator between things, is there a way to study the imperfections of timing, either within a simulation, a coherent one, or how imperfections in timing, either deliberate or inadvertent, can affect the physical outcomes, not the modeling environment, but the physical outcomes of interacting systems?
So I think the answer to that is yes. It'd be a tricky experiment to set up, but I think you could, because basically you would then want to represent the wall clock, which would be the Helix core, would be kind of ticking along, representing the physics. You'd have each of the modules keeping along with the physics of the system, right? So you keep those would never have any time skew. That's the physics, right? Yeah. But then you'd have a communication pathway that would skew the time within there. So that's built in. Actually, you can do that directly into the core part of Helix. Phil and his team built a great kind of communication layer in there directly, so that you could represent failure rates and skews of time and things like that. And so you represent that logical layer as a separate layer. And so that your PMU or your sensor or whatever it is that's using these kind of sources for GPS, they would think it's one time and they would react that way, but the physics would say it's a different thing, and so they would basically then react to it according to reality. And so I would certainly want to spend a little bit of time validating that and make sure we got it right, but I think that's an experiment that could certainly be done.
Yeah, and it's like even within, like I always go to the distribution system, but it's like the clocks that are on the on smart meters and things like that, they're good, but they're not awesome. And so and for most operational timescales, it really is truly irrelevant. Certainly for billing, it's completely irrelevant unless you can go off by a month or more. But is that there are these imperfections, and so we're talking about sort of frequency coordination and stuff like that, is that the qualitative aspects of available time references within the domain and across domains can have effects, and I really don't know what they are.
And I think in some ways you could probably use some of the hardware in the loop capabilities that have been developed over the last couple of years. That would be something that you could actually probably set it up in a way that you could actually plug in, say, a physical device, and then use Helix to pump in the signals that would say be your clock, right? So you could actually replicate those kind of events through a piece of hardware if you really wanted to dive into the hardware piece of it, or through an emulated piece of hardware.
Great. So that's the end of my question.
Awesome. Well, thanks so much. Thanks everybody so far. We're at a really good point to transition to our first presentation. So as mentioned before, I'm going to go ahead and stop this recording and start a new recording. And Adil, if you want to work on bringing up your presentation, you'll be up next.